One of the most important applications of a loop in a magnetic field is a DC motor. The way a DC motor works is you put a loop inside a magnetic field, and that loop will be connected to a circuit so that there can be a current inside it. It's worth mentioning that these magnets here are just examples of the type of magnets you might see in a DC motor. The geometries of them can vary quite a bit. But even though it's not shown, each magnet would have a north and a south side. And so let's assume that we have a nice uniform magnetic field between those permanent magnets. We can get a current flowing through our loop as long as we connect the positive side of the battery to one end of the loop. And if we did that, then current would want to flow in this direction from positive to negative. And then it comes back to the negative side of the battery. There has to be a split in this ring here. It's called a commutator ring, because we don't want to short circuit the loop. We want to force the current to go all the way around. So that's one reason we need a gap there in our ring. Next, we want to use our principles of current carrying loops in magnetic fields to find out what the forces would be like on different sections of this wire. So to do that, we'll use our right hand rule. We can point the pointer finger in the direction of current. We'll have our middle finger point to the right. And our thumb will point downward. So current flows this direction. The B field is to the right. And the thumb shows that our force on this part of the wire will actually be downward, like this. If we try the right hand rule on this segment, we'll find that the force is 0 there, because the current direction is opposite the field direction. Then we can try it here once again. We'll have this. Pointer is the direction of current. Middle finger is the B. And we see that the force on this segment of the wire is directed upward. In this section, the section closest to us, the force would be 0 because the current would be traveling in the same direction as B. These two forces, though, are very consequential for what will happen inside the motor. As it carries the current, it's going to feel a torque. That loop is going to want to twist. It's going to want to spin. And this is where we'll get the mechanical energy. And so that loop can be connected to a shaft, which can do work through the torque that it exerts. Okay, now, what will be the direction of torque here? So here's our axis of rotation for the loop. And it wants to twist clockwise. So the direction of torque will actually be back in space. It will be in the negative z direction. We should also draw the magnetic moment mu. By the right-hand corkscrew rule, the magnetic moment mu will point up in this direction. The magnetic moment mu wants to be aligned with the external magnetic field. And right now, the external magnetic field is pointing from north to south. It's pointing directly to the right. Our mu is not pointed to the right, though. It's 90 degrees to the magnetic field direction, which means that mu really wants to rotate right now. It's going to feel the most amount of torque that it can feel in any given position because it's at a right angle with the B field. That's when we get the maximum amount of torque. So what happens in other positions for the loop? We know that our loop is going to want to rotate this way, clockwise. So it's going to be in this position here before it gets to this position, and then it'll finally move to that position. All right, so what happens to the current inside our loop as it makes that transition? So as we can see here, if you look very closely, the bottom part of the commutator ring is still in contact with the positive side of the circuit, which means that current is going to flow this way through the wire. It'll make contact with the lower part of the loop, and current will continue to flow in this direction as long as there's contact with the commutator. And eventually we come back to the negative side of the battery. So here we find that the force acting on the lower section of the loop will actually be directed straight downward if you do the right-hand rule on it. And this part will acquire a force as well, but that's going to be directed back in space. You can do the right-hand rule on the top segment and you'll find that the force is up. And here, even here, we'll have a force directed in the positive z direction. This doesn't give us much net torque at all. Just a little bit because of the slight angle that it's at. So we're almost at zero torque here. So if the loop had already been in motion, then it can just continue to coast into the next position, which would be number 2 here. Now we should also draw the magnetic moment of this loop. So the torque is approximately 0 here. If you do the right-hand corkscrew rule on this loop, you'll find that the magnetic moment is almost perfectly aligned with B. And this is one explanation for why we don't see a lot of torque, because the mu is almost where it wants to be. It wants to be aligned with that external magnetic field. Now this loop can continue to move of its own momentum through positions 1, 2, and then 3. But in position 2, we see that the commutator ring is no longer making contact with the circuit. So current will stop for a brief time. Since there's no current in the loop, we won't have a magnetic moment to draw. In position 3, we see that a new part of the commutator ring is touching the positive side of the circuit. And so as current flows through the circuit here, it's actually going to connect now to the top part of the loop. And so current is going to switch direction in that loop and flow this way. Eventually, it makes its way back to the negative side. If we do the right-hand rule analysis on this situation, we'll see that the force directions have reversed. Now the forces will be pointing inward, like this. Once again, we don't get a substantial torque in that position. But one thing that's interesting that does happen is the magnetic moment direction is now switched. When we do the corkscrew rule for the magnetic moment, we should find here that it points to the right. And that is the direction of mu. But when we switch the direction of current, the fist has to switch as well. And now we're going to get this direction for our magnetic moment. This switching of the direction of the current is critical to making the rotor continue to want to twist in the same direction. Otherwise, it would really just oscillate back and forth. We wouldn't be able to get any net work or net power out of this motor. In this position, the mu is almost 180 degrees opposite the field, and so it wants to be aligned with the field. So now the magnetic field can do all this work in pushing the rotor all the way around once again. One way to keep track of which side of the rotor is where is we can just shade in one edge of it. All right, so in this position, the black part of the rotor is about to go downward because that's going to be the direction of the torque. The torque's going to make it want to twist downward. The force there is going to want to pull it downward. So this part of the rotor is going to be the black section. Now, when it continues to make its revolution, there's going to be a slight torque on it to make it twist clockwise again, because mu wants to align with B in the shortest way possible. So the black segment of wire here will now be located on this side. And current will be flowing toward us. And so our magnetic moment in this position will be located up, just like it was originally. Okay. Here, our black section is now on top. Our our magnetic moment will be almost perfectly aligned with the field like it wants to be. But then the commutator will cleverly switch the direction of current to make the mu opposite the field once again, and the whole process just keeps going.